I'm Chelsea Fortin, and I'm a technical assistant in the Bhatia Lab at the Koch Institute. And the Bhatia Lab focuses on using engineering to combat medical challenges. So in addition to using nanotechnology to try to learn more about and treat cancer, we use tissue engineering to try to combat the growing problem of human liver disease. So the largest burden of liver disease is in cirrhotic liver disease, where the liver is so damaged that it can't regenerate itself. We said, what if we could create a satellite liver and implant it near the liver in the abdominal space, but not on that diseased liver, because the cirrhotic liver is going to be inhospitable to healthy cells. Big problem in tissue engineering with complex organs like the liver is that they're very large, they're very thick, and they need a vascular structure. They need blood vessels to supply nutrients. So for example, if you engineer a tissue and it gets thicker than 1 or 2 human hairs, the core will start to die from lack of nutrient diffusion. So we decided to combat that problem by micropatterning blood vessel cells and laying down the groundwork for the host body to take over and create a vascular system of its own. So to micropattern our blood vessel cell structure, we take cells from blood vessels, from human, and we spin them into a micropattern mold that creates channels that are the width of a human hair across. And then we create micropatterned aggregates of healthy liver cells and fibroblasts. And we combine our micropatterned blood vessel structure with the micropatterned aggregates of liver cells and fibroblasts. And then in an in vivo model, we cause liver injury. And over time, our little seeds expand more than 50 times. So this image shows one of our implantable satellite livers. And in the red, we have human liver cells, or human hepatocytes, which we have implanted. And in the green, we have our human blood vessels, which we have also implanted. And the white dots are the mouse's own blood cells. So we have our implanted human vasculature system, which is being perfused by the mouse's own blood. It directly addresses the problem in tissue engineering of vascularization, because we can implant these satellite livers, and by harnessing the mouse's own regeneration cues, we're able to cause the tissues to expand, and the vascular system grows with the tissue. So we're hoping that we could use these tissues clinically to give a patient who's waiting for a transplant a bridge to treatment. Because there are 17,000 people right now on the transplant list, but there are only less than 7,000 transplants happening per year. So we're hoping we could one day use these tissues to help get people to where they can receive a transplant. But we're also hoping that this work and these tissues will help shed light in the field on how liver regeneration occurs, what's going on biologically behind these tissues expanding, and how can we as bioengineers harness that and make these tissues even more clinically relevant.